Bismillahirrahmanirrahim. Assalamu alaikum. So today we are still going to continue with the reverse osmosis. In last lecture we started with reverse osmosis, and as we discussed that the outlines for these two lecture include all these points, which is introduction of reverse osmosis, mechanism of reverse osmosis, then its application for various separations, as well materials and modules used for reverse osmosis on industrial scale. And the last part of this main reverse osmosis topic is about design of reverse osmosis system and important parameters. So quickly I will just recall all the points which we have discussed yesterday. That initially we studied osmosis, and then we said that how it's related to reverse osmosis. So osmosis was traveling or movement of solvent through some semi permeable membrane from low solute to the high solute concentration, and we said if we apply any external force against this natural force, then we can reverse this phenomenon, and that's called reverse osmosis. And reverse osmosis is actually based on your book. Osmosis is not separation technique, even it creates mixing. So we have to go in the reverse of this, and for that you have to apply higher pressure as compared to the pressure on the other side of the membrane, as well as osmotic pressure. You have to overcome all those pressure, and then you can go for reverse osmosis. And then we said that most of the reverse osmosis membrane are asymmetric membrane. Why? Because you have very high pressure on the both sides of the membrane. To for this phenomena you need some actually dense membrane for reverse osmosis, and dense membrane will be a like one sheet, very thin sheet that can't support very high pressure on both ends. So in order to avoid the rupturing of membrane, we make membrane as asymmetric membrane. Its top layer is like dense membrane, and below that there are porous membrane. Micro and macro porous membrane can be used, and they are just used for separation purpose, for support. Sorry, not separation, they are used for supporting. Only the top layer, which is active layer and which makes separation. So in order to withstand this high pressure on the both sides of membrane or transmembrane pressure, we use this. And most of the time this RO are used, or reverse osmosis systems are used for cleaning of water. Now here we have studied different type of water coming from sea that contain very high amount of solvent, even that's 3.5% or 35,000 ppm. And then there is brackish water that has salinity or salt content between sea water and fresh water, and fresh water actually contain 500 ppm dissolved solids. And then there is wastewater. Wastewater is actually water coming from all human which is contaminated with various pollutants due to human activities. Those include industrial, domestic, agricultural and all commercial activities. And then we said that actually before 1980, mainly for desalination purpose, flash distillation was used, and that's flash distillation actually involve high temperature. You have to heat the water, and you boil water, and salt are left on the surface of the equipment in which that water was contained, and then water which is boiled is condensed. That was highly expensive technique because it involved large amount of heat. So that was replaced with the efficient membranes in 1990. And recently a lot of plants are used in the world. Around 1000 plants are used, and they are producing daily 750 million gallon per day of potable water. Then we looked at that majorly spiral wound and hollow fiber membrane modules are used because they can withstand high pressures as well. There are cellulose acetate based and polyamide based membranes are used for these separation. Although both membranes suffer from some problem, but they can be overcome by pre-treating the water. And then as we said, water contain a lot of impurities. There are not only salts which can be rejected with the reverse osmosis membrane, so some of those can be even separated before bringing it to the membrane. And why we separate all this stuff here, we discussed that you can use either various type of other porous membrane like micro, ultra and nanofiltration membrane to remove some of those contaminants, and sometimes you can also use various other processes like flocculation, filtration, there is ozonation, chlorination, these oxidation and adsorption. These are various other pre-treatments which are used before bringing the like water for final touch or for final removal of monovalent ion. Actually these monovalent ions, for example NaCl, KCl, the majorly is NaCl, as I told you yesterday, that's the major constituent of seawater. So and this reverse osmosis is mainly used for desalination plants as well. It can be used for various other water treatment plants, but mainly for desalination plant. Due to this I am talking about these monovalent ions. So these monovalent ions cannot be effectively treated or separated by using any other technique like these porous membrane or even adsorption and all other technique which we have seen, ozonation, chlorination, those techniques. So that's the only solution, reverse osmosis membrane or distillation by heating the water and precipitating or separating the salts. So as we said that distillation is more expensive, so due to this we go for reverse osmosis. And in this reverse osmosis final stage only these membrane are dense membrane which allow only water to pass through, and monovalent ion which are solid, they are just separated here. So we also discussed this system that does somehow the same stuff but in the form of like PFD, in which you can see that feed water tank, from that it is pumped to some pre-treatment unit, and that can be more than one pre-treatment unit as shown here various. It is not necessary always to have all these units, but sometimes you can have like 3, 4 or 2 or 3 of these units most of the time. And then you go for high pressure pump, and that's high pressure is generated actually to just get permeate or high amount of permeate through the membrane. And with this we finished last lecture up to here, and at the end I advise you to just go through the textbook. There he has explained the use of actually reverse osmosis membrane for various treatment plants like textile industries and many other chemical industries for wastewater treatment. So just quickly go through them, and actually you should have the idea that where reverse osmosis can be used. For desalination definitely it is being used for various industries where it can be used. So many example he has provided, I think 8 to 10 examples are provided in your text, kindly just look at them. So let's start with today's topic, that's reverse osmosis membrane system design. As I finished yesterday my lecture at this point, so I told you that there are various factors which you have to keep in mind, or various calculations which you have to make while when you are going for like designing of this system, RO membrane system. So those calculation involve solvent flux. Solvent majorly it will be, if we are using for desalination purpose it will be water, otherwise if you are using membrane for any other separation, these RO membrane, so then the solvent that species will just permeate through the membrane and is obtained as a permeate, that's solvent. Its flux calculation mean how much amount is passed or what is its flow rate per unit area. Its calculation, then there is salt flux is sometime, as I told you, mainly reverse osmosis membrane are being used for industrial plants due to the for desalination plants. So due to this major calculation which we are going to look here are stuff that deals with the solvent, like it will be water and salt which are present in the water. As I told you in last lecture that these membrane are not only 100% selective for water, they can also allow other contaminants to pass through, but they pass like in very small amount. In today's lecture we will look like salt can also pass through that membrane, but they are passed in very small amount. And this salt flux calculation, that how much salts were passed through the membrane, and then this salt passage or rejection. These are the factors which are also calculated or used in calculation. So rejection mean how much were rejected, and passage how much passed through this membrane along with water or the solvent. Then pressure drop across this membrane, that's also important parameter, and then finally there is concentration polarization. So let's look at them one by one. Here I will go through them, major formulas and their calculation. We will not go for their derivation mainly. There are few steps which are actually missed, but major steps are given here for calculation purpose. So at least you should know how to use these formulas and what are the terminologies involved in these formulas. If you recall few days back when we started with the membrane separation, there we studied that actually permeance or this passage or flow of solvent through the membrane depends on two parameters, that was permeance, and permeance was permeability divided by the thickness multiplied by driving force. So here majorly for this system, when you are using it for desalination purpose, mainly the major transport or force here, driving force, is actually pressure difference across the membrane, and that's delta P here, pressure difference. As we said that this is transmembrane pressure, suppose it was 2 cells, so there was a membrane, and across this there is P1 minus P2. So if you just take this difference, suppose P2 side is the pure solvent or pure water, and P1 is the solution side, so here P1 minus P2 is the main difference in pressure. And we said that then there is osmotic pressure on both sides. If this is pure solvent, on this side there will be pi will be 0 as talked in last lecture, and here on this side definitely it is solution, salt will be there, so there will be something some value of this osmotic pressure pi. Here delta P must be greater than delta pi for reverse osmosis to occur. Yesterday also we discussed this point, that pressure here should be higher, P1 should be sufficiently higher for this passage of solvent through the membrane and for this reverse osmosis to take place. For desalination purpose, when you look at brackish water, so this pressure actually across the membrane or delta P value is between 400 to 600 psi. As well for seawater it is 800 to 1000 psi. This is a huge pressure which you have to apply across the membrane. Like suppose you are getting water on this side of maybe just at normal pressure of 1 atm or 14.7 psi, so on the other end it will be very high pressure. And most of the time here, if I talk about in atmospheric pressure, so it is like somehow it will be around 20 to 30 I think psi, and the other end it is usually 2 to 3 psi. Just another thing in your book is also provided related to this. He has provided various exact example for this, that if you are looking for some separation of brackish water or seawater, so how much should be pressure and how much salt are recovered and how much permeate you get. Just go through that for your information. That's also available along with the examples of membrane, RO membrane for various industrial plants. That's on the same page. So rate of mass transfer of membrane, this water, solvent or water through the membrane, that can be calculated. Actually the solvent flow that can be calculated by using the same equation which I just started with. I was telling you that was flow of or number of moles of some fluid solvent passing through the membrane is equal to this terminology was called as permeance, that is permeability of that component through the membrane. That component is here water, because we are talking about water, so this component, this will be molar flow rate of the water, and this will be like somehow permeability of water through the membrane and for membrane, and then there is thickness of membrane, and this is driving force delta P minus delta pi. So there is I think derivation of this equation in your book, but no need to go through all that. Just remember this formula and use it. So here delta P is actually indicates pressure, hydraulic pressure difference, so pressure on the feed side and permeate side, so that can be measured, and we will have it like delta P which can be calculated. Then there is osmotic pressure. So osmotic pressure, that's again delta pi. So one side is feed side, this from where feed is entering, this he is calling as feed side, and other is permeate side from where permeate is leaving. So same for pressure on the feed side minus pressure on permeate side, and this osmotic pressure on feed side minus osmotic pressure on permeate side, that's delta pi. Then there is, as I told you, this permeability. This is the membrane property, and most of the time we get it from experimental data that's provided usually based on interaction of any component, like here water with the membrane material, and thickness. And most of the time, in your book this is given as a complete permeance value, that's permeability divided by thickness, that's given as a permeance. Here this if you have to calculate osmotic pressure, so that can be calculated, like suppose if permeate side, on permeate side it is pure solvent, and you know when it is pure solvent there will be no like salt or no solute there. So as yesterday we saw that journal formula which can be used for this, that was equal to pi is equal to mRT, and m is molarity, that's number of moles of the solute, and when there is no solute, pure solvent, then it will be like 0. Due to this he said that pi of permeate, osmotic pressure of permeate, then in this specific case of pure solvent will be equal to 0. So here in your text there is one equation provided for sea water, one correlation provided for sea water calculation, because that's dependent on many factors here. So they have provided, because sea water, as we have seen yesterday, that sea water salinity varies, so that's one correlation given here in the book for sea water osmotic pressure calculation. Like suppose you are given that seawater is entering to the membrane on feed side, you can calculate this pi. As well you can use this same for the permeate side as well as for feed side. So that's equal to 1.12 T into summation of molarity of all components. So overall, suppose there is one component, for example water contains only NaCl, so it will be only molarity of that NaCl. And then if it is like more than one component, for example there is also KCl, so it will be sum of the molarity of that component. And one thing remember here, when you have to use this formula of molarity, this is sum of the molarity. Suppose you have NaCl, so when it get dissolved inside water, so what will happen, it is broken down into two ions like Na plus and Cl negative, this just split into its ion, Na plus and Cl negative. So actually we will calculate molarity of Na plus molarity of Cl. It is not of the compound, it is based on each individual component. So if Na and Cl, so overall they are same, like 1 mole of this is produced and 1 mole of this. So overall if we calculate the molarity of one, we can just add it up to get the molarity of both. But if also there is like something KCl, so there will be 1 K and 1 Cl, again same. But for example you have CaCl2, so in this case number of mole of Cl2 are double as compared to the calcium. So its molarity, when you have to calculate, for example for calcium and for chlorine, so then you have to add them up. So overall this equation can be used for calculating osmotic pressure across the on the both sides of membrane, on feed side as well as permeate side. And we will use this in one of the problem today we have to solve at the end of this lecture, so you can see the utilization of this equation. So here but a few things are necessary to remember when you are using this equation. Here units are very important. Pi as per this overall correlation at the end of the day. Here what we did, actually you can see that R was replaced, you don't need to worry about the values of R, and this correlation maybe was derived in order to avoid this problem of R, because sometimes you can get confused with the units and that stuff. So based on this, here value of R is already inserted in the equation, and this final correlation is given which you can use. So pi is in PSIA, pound per square inch absolute, and T is in Kelvin. Here when you have to use this equation, use T in Kelvin, and this MI sum of molarity of all components, that's the summation of molarities of dissolved ion and non-ionic species in mole per liter. Suppose there are ions and sometimes there can be impurities which are even non-ionic, but they are available inside the system, so they will also be calculated, and this final unit of molarity is actually in mole per liter. For example, you are using this equation and you calculate molarity yourself, so just convert it to mole per liter. I think we will also make such conversion when we are going to use this equation today, but take care of the unit, like pi should be in psi, T in Kelvin, and this in mole per liter. So this was equation for solvent flow calculation, and I have explained to you the various terms inside this. So most of the time pressure, this maybe you will be thinking how to calculate this pressure across the membrane, is most of the time provided, or you can see that we can actually measure this pressure across the membrane by just inserting like pressure gauge. But this osmotic pressure, that's due to salt you have seen, and due to based on temperature. So you can see this salt are accommodated here in molarity, and temperature is available in its relationship. So that's calculated by using equation, and most of the time when you are designing the system you have to calculate. Other is salt. We said that another second parameter, that salt calculation, and salt flux is calculated through some equations. They were already described in some section which we have skipped of mass transfer, that, as I told you, that was not related to you or your course, but one equation which can be used for salt flow calculation in this section, even for RO. So that's this equation, same equation. So I will just explain this because they are similar. There are just few based on given concentration, this equation can be modified, like here that's Ci naught and CIL, but usually we have feed and permeate and their concentration we also calculate, because concentration, actually molarity is also a unit of concentration. So when you will be calculating here the molarity for solvent flow rate, definitely you have calculated this molarity, and that can be used again in this equation. Due to this, I will adopt this part of the equation. I will not use this equation. So you can just skip this equation, just look at this equation here. Overall you can see again, for any salt component, if you are calculating its flow or number of mole through some membrane, so that will be equal to, this is again here the permeance, that's permeability divided by thickness of the membrane. Here permeability is actually given in terms of mass transfer coefficient and diffusivity. As other are here concentration on the feed side of the that component as well as on permeate side. So for here like PMI, this permeance is permeance, this is permeability, term which is in numerator, that is permeability, and permeability over thickness is actually permeance. So we are talking about this numerator, that Ki Di is the permeability of solution diffusion model, where Ki accounts for solute solubility in the membrane, so, and Di diffusion through the membrane. So if we know these values, then we can definitely calculate this permeability, and then permeability that will be used. So these are also measured based on the experimentation, diffusivity and solubility of various components through the membrane. So all membrane system, usually when they are developed, they are tested on the lab scale, and all this data is collected, then that is used for designing the system on large scale. So this Di and Ki and therefore PMI, they depend on the solute and membrane. As I am telling you, they are not specific, they are not like only journal formula for them. So you have to look at the interaction, diffusion, solubility of various components through the membrane, and when you will change the membrane material, you will change the solute, these will change actually. So that can be obtained from that data, and then they will be used for making these calculations. Otherwise sometime you are directly given the permeance based on, that's also definitely based on the experimental data for any membrane. So it is not necessary that in some problem you are not given like thickness, you are not given Ki and Di, that's direct permeance is given. So that's fine, that's really easy for you to use directly permeance here and multiply it with the difference of concentration, and you can get salt flow rate. There was one term, salt rejection, which we said is important. Salt rejection, what does this mean actually? Before we go for salt rejection, we look at the salt passage. Here, as in the last slide we saw that we are calculating the flux of salts through the membrane. As I explained to you that membrane are not 100% selective for solvent only, they can also allow some of the other component to pass through, and here salts which are solute that can also pass through the membrane, and their flux can be calculated by using this equation. As well, passage of these salt can be also expressed in terms of our flux of these salt, that can be expressed in terms of another main term that is called salt passage, SP. This represented with SP in your book, salt passage, and that salt passage can be easily calculated if we are just looking, for example, the fraction of salt which has passed through the membrane. So that's like concentration of salt on permeate side over concentration of salt on feed side, and you know that if we know or we have these two values, salt passage can be easily found, that how much percentage, if we just multiply it with 100 we can calculate percentage, otherwise its fraction can be found. And when you know that suppose if you know the amount of salt on feed side, suppose we just consider it that's 1 or 100%, so some of that portion has passed through this membrane. For example, 5% has passed, so overall how much is rejected or not allowed to pass through the membrane, that's called salt rejection. Mean all those salt which was rejected, which were not allowed to pass through the membrane, so that is represented with SR is equal to 1 minus SP, and 100% like SP how which was passed, suppose 100 minus 5, it will be 95% salt are rejected. So most of the time membrane which you are using, they like don't allow much salt to pass through. They sometimes you can find 2 to 3 to 5% salt can pass through the membrane, all other are rejected mean. And definitely the membrane which will have more salt rejection will be more good membrane, because we want to separate solvent from these salt, and if they can't pass through the membrane, definitely that membrane system is good, right? Next topic is related to concentration polarization. So what is concentration polarization or important factor across this also appeared in the lecture about membranes, I think in this week. So concentration polarization, as its name indicate, polarization, creation of some pole, something like charge. So concentration polarization occurs when the concentration of specific component increases or decreases at the boundary layer close to the membrane due to selective transport through the membrane. As we know that we only allow, or we are looking for solvent to pass through the membrane, so all salts will be rejected at the surface of membrane, so they start building, and when they are building at the surface, definitely they, if they are not removed through the system, so their concentration is increased, and this phenomena cause actually concentration polarization. And it is important, why? Because we have seen that osmotic pressure across the membrane, that's highly dependent on the salt concentration. If salt concentration is increasing inside the system, so that will increase the osmotic pressure, and membrane performance will decrease. So due to this, it is important to calculate or look at this concentration polarization, and that concentration polarization can be calculated, or there is again derivation for this, quick derivation, but we will look at the final expression that can be used for calculation of concentration polarization factor. So that's represented with this symbol. So that's something, concentration polarization is equal to, like these are again concentration of any component, at interface something feed, and again concentration of those salts inside feed as well as at the interface or boundary layer. So this is again difficult to find or calculate. Okay, one thing here actually, this concentration CSI is as it is difficult to measure, so that's another replacement formula here. That's about flux of solvent through the membrane, which you have already calculated. Salt rejection, that's also calculated by using salt passage, and then Ks, that's this salt mass transfer through the membrane. So this formula can be used to calculate this concentration polarization. So when you are designing any reverse osmosis system, it is important to calculate this parameter for your given system based on your requirements. So value of usually salt rejection are between 0.97 to 0.995. This mean salt which only pass through the membrane range from 3% to 0.5%, otherwise 97% to 99.5% salt are rejected. And if concentration polarization value is greater than 0.2, then concentration polarization is significant and it will create high osmotic pressure. Due to this, you will need to design the system or change the system in which will reduce concentration polarization. So when you make calculation and its value is greater than 0.2, so it's important to remove those salt to reduce the concentration polarization or change the design of your system. The last parameter which is important, that's about pressure drop. And in pressure drop, actually this feed side pressure drop is important, because we have seen that that's the major cause of driving force through this membrane. So if pressure drop is higher through the membrane, so then there will be problem. The problem, actually, it will not provide you sufficient permeate or the separation which you are looking for. But as we have seen here, sometime you have seen that pressure drop can be calculated for various equipments through even columns, through as we have seen plate tower, through packed column. But through this membrane system, especially RO membrane system, it is difficult, because there are difficult geometries of spiral wound and hollow fiber membrane. So the equations are difficult to manage, and they can't predict good pressure drop calculation through this RO system. So it's better to estimate pressure drop from experimental data, like you perform the experiment on lab scale initially, and then just extrapolate that for large scale plants. So feed side pressure drop for spiral wound module and hollow fiber module range, there is some range, like it should be like in, if you are using spiral wound, you know that spiral wound modules, there are the sheets which are rolled, and then there is one tube at the center of these rolled membrane. So that's a complex system, and in that pressure drop is high. It is allowed like pressure drop from 43 to 85 psi, while in hollow fiber module that's less. Actually, they are hollow fiber, very small fiber. There are very small holes through those fiber, and this separation takes place, and there it is only 1.4 to 4.3 psi. So just overall you can remember quickly to this, like it's around 40 to 80 psi, and it's 1 to 4 psi. So that's not calculated. Due to this, when we are going to start this problem, in which we will not calculate this pressure drop, but all other we will look at those parameters that we have to calculate. So here I am going to discuss this example quickly. So I have tried to make it simplified as compared to the solution provided in the book. So let's proceed with this. Actually, in this example, by the way, up to here we have discussed major important parameters which are considered during design of the membrane, RO membrane system. So they include solvent flow rate. You have to calculate permeate solvent which passes through the membrane, for example water flow rate, as well as salt flow rate through the membrane, then salt passage or salt rejection calculation, and actually we are calculating it to calculate finally concentration polarization across the membrane. So let's look at this example here, that that's about calculation of polarization factor in reverse osmosis. At a certain point, there is a spiral wound membrane, and you know that when we are using these membrane, there are various modules and number of modules. But here he has provided for, like suppose there are many spiral wound modules, they are being used as a RO filtration plant or RO membrane plant. So in that you are making calculation at certain point. At a certain point in spiral wound membrane, the bulk conditions of feed side are, if you look at that system, in that system feed side conditions. Feed side condition mean feed, what are temperature, pressure and composition of the feed. So that feed contain 1.8 weight percent NaCl. So as I said, as I told you that most of the time reverse osmosis membrane are used for desalination. So here he has provided us actual example of desalination, and in this you can see that he has only provided you the only NaCl concentration. Rest he didn't talk about anything else. So later in this problem he will talk about water, but like here 98.2% will be water, 1.8% is NaCl, and 98.2% will be weight percent. Based on weight percent, that will be water, and this is available at 25 degrees C and 1000 psia. While bulk condition on permeate side are 0.0 weight percent NaCl, it's mean only this 0.05% NaCl passes through this membrane. It's mean 99.5% water will be there. At it is available at 25 degrees C. Mean temperature is same on both sides of membrane, but pressure has highly reduced. It is only 50 psi. On the other side of this, it is only 50 psi. Then there is, for this membrane, the permeance values are here, they are also given like directly. Permeance value for water is given, that is 1.1 into 10 to the power minus 5. That was actually permeability divided by thickness of membrane. So that's directly given to you as a permeance for water. And also 16 into 10 to the power minus 6 centimeter per second for the salt. Mean salt NaCl permeance for that is also given. So that's good, like directly you are given with the permeance. You don't need to go for permeability and thickness and all those calculation of K and D and all other stuff. If external mass transfer resistance are negligible, here no mass transfer resistance is mean external across the system. So calculate the flux of water. We have to calculate flux of water, and he has mentioned the unit in gallon per foot square per day. And then there is flux of salt. Flux is flow rate of something per unit area of the membrane. So it is gallon per day, flow rate of water per foot square of the membrane. And then salt, salt is measured in gram. That's solid stuff, so that's in gram per day per foot square. That's salt flux. We have to calculate in gram per foot square per day. If Ks, that was 0.005 centimeter per second, estimate the polarization factor. So overall you can look at this based on this given data. Finally we have to calculate 3 parameter, that is flux of the water, flux of the salt, and concentration polarization. These we have to calculate. So let's start with the solution of this problem. First of all, okay, let me tell you here, you have to use 3 different formulas, which will be used. First of all, a formula for flux of water, then flux of salt, and then there is concentration polarization. So here I have provided those, but the first one, the formula which we discussed for water flux, that's not appearing here properly. So that was N of water is equal to this was permeance multiplied by driving force, and that driving force was delta P minus delta pi. Out of this, permeance is already given to you. Then there is delta P, pressure on the both sides of membrane is given, so this can be easily found. Then there is delta pi, that's osmotic pressure, and due to this I have provided you the equation which we have already talked. This will be used for this calculation. And then this formula will be used for calculation of salt, flow rate, salt passage, salt flux through this membrane. So that's permeance. This parameter, as I told, this is permeance, so that's already given. So what we will need concentration of feed and permeate side to calculate this salt flux through this membrane. And then finally you have to calculate this concentration polarization. So you can use this formula, this side. So that's flux of water, when we have calculated in the first part, that can be used here. And then there is salt rejection. So salt rejection will be calculated by using Sp is equal to 1 minus Sr. and SP can be easily calculated because you know that SP was just the ratio of concentration on permeate side over concentration on feed side. That can be easily found as we have already calculated this stuff. So SP will be calculated with this SR, and this KS is given. So these are 3 or 4 formulas which you have to use for these calculation. So initially let's start with the calculation of water flux. For water flux, if you look at this formula, as I told you that in this permeance is given, delta P is given to you, then the only thing which you need to calculate, or you should know, that's delta pi. And for delta pi, it's mean that is pi on the feed side minus pi on the permeate side. So you will need pi on both side, permeate and feed side. And in order to calculate this pi, you know that here as per this formula you will need to calculate molarity on both side, mean feed side as well as permeate side. So let's look at this. For flow rate of the water, we have to calculate concentration of molarities, and that unit is mole per liter for feed side and permeate side, which I have just explained to you. For this calculation, so how we can calculate molarity on the feed side, that is equal to actually number of moles over number of moles of salt actually over volume of solution. This is the formula for molarity, just remember. Kindly I am explaining this in the book, it is not too much clear, so just look at each and every step carefully so that you can later solve other problems. So number of moles, how we can calculate number of moles of salt? Do we have any amount of salts here? Yes, if you go back to the question, so based on given data there was 1.8 weight percent NaCl. If we take it like 100% feed side, mass flow or percentage 100%, so it will be like 1.8%, or if I consider it as like 100 gram on feed side, so 100 out of 100 gram NaCl is 1.8 gram, and other like 98.2 is water. So let's use this 1.8, this number of mole, you know, number of mole is equal to mass over molecular weight, and for NaCl you know this molecular weight is 58.5 and 1.8 gram NaCl was there. So from here you can calculate that it will be like 1.8 gram divided by 58.5, number of moles of salt are calculated. Clear? Then there is volume of the solution, and solution here is based on the water. So we can calculate volume. Can we calculate based on the given data? Yes, somehow you are given some information, and that's amount of water based on this percentage, that's 98.2 gram. So we can use that. If we have the mass of water, we can just divide it by the density of the water and we can calculate volume. By the way, here some of you will think about it, that's volume of solution, but we are using the volume of the solute. Actually, if we just consider even this small amount of this NaCl, its amount is also accommodated and its density, so that will not make big difference. So due to this you can directly calculate this volume of the solution based on volume of the solvent, that was water. If you have to look for exact accurate calculation, then definitely you will need to include this for volume of the solution, so that will not make big difference. Actually, if you have to even include that, that will not make big difference. So we are directly using only the solvent water. Water is 98.2 gram and its density in these unit is gram per liter, that's 1000 gram per liter. And here even you can start with that 1 gram per cubic centimeter, so you will finally reach to this point. Why? Because at the end of the day this molarity should have unit of mole per liter, so due to this I am using this density value. So overall this gram will cancel with this gram as well. On numerator side this gram will cancel with this gram, and finally your units which are left are gram per mole and its value is 0.313. So you can check this calculation. Then finally when you have calculated this molarity on feed side, so now that can be used for calculation of this pi. because if there is only 1 mole NaCl, as I told you, if for NaCl 1 mole you are producing actually Na plus Cl, these are produced. These are this equation I already told you that that's based on components of salt. So NaCl is giving you Na plus Cl. So here, as we have calculated for molarity of NaCl, so that will give you Na plus Cl. So there will be, if you have to look for this Na and Cl, their amount, so that will be 2 times NaCl, because this one is giving 1 Na plus 1 Cl. So based on this, we can use this value of pi to calculate this. Pi is equal to 1.12 multiplied by temperature, as you know that temperature should be used in Kelvin. So multiply by this 2 indicates like Na plus Cl, these are 2 ions are generated here, multiply by 0.313, the molarity of 1. So multiply by 2 because these are 2, and overall you will get it like 209 psia. And finally we have converted it into atm. Why? Because there is atmospheric unit somewhere in permeance. Here you can observe there was some unit of atm. So due to this, I have just converted that value from psi to atm. Next, same process will be adopted on the permeate side. So on permeate side, number of moles over volume of the solution and number of moles of the salt. Again, there you have like 0.05% salt, that is equal to 0.05 gram if we consider of like 100 gram here. So divided by its molecular weight, and similarly then 99.5% is water. So 99.5 gram over its density, mass over density, that gives you the volume. Again, here we are ignoring very small amount of salt, and we are considering volume of solution is equal to volume of the solvent. So that's 0.086 gram mole per liter. The same process. And again, here again on this side you have to calculate permeate side pi, because that finally you have to calculate delta pi. So it will be equal to 1.12 multiplied by 298. Same mean temperature was equal, if you remember from the given data, it was 25 degrees C on both ends of membrane, or both sides of membrane. So multiply by, again here NaCl is dissolved into Na and Cl, so it is 2 times this molarity of NaCl. So that's 5.7 psia, or equal to 0.4 atmospheric pressure on this here one thing you can observe, that osmotic pressure on one side, feed side, because there is very large amount of salt, so it is higher as compared to this. On this side it is very low. So if it was suppose pure water, there was no salt, so it should be definitely 0. We don't need to calculate this. Now as you have pi on feed side as well as pi on permeate side, so you can calculate delta pi by using these two values, 14.2 and 0.4 atm, and it's 13.8 atm. So then in this equation, another unknown left is delta p. Even you can calculate that before starting this, but here I have calculated delta p, so that's equal to 1000 minus 50, and that's equal to 950 psi. And also convert it into atm, so that we have all same units. Now up to here you have all unknown for this equation. You have calculated, the main calculation was related to pi, calculation of pi you have done, as well as you have delta p, and permeance was given to you in the main question. So you can calculate flux of water, and for this flux of water we will have like the same equation. This first one, flux of water. So flux of water here will be equal to permeance, this factor permeance, multiplied by delta p minus delta pi. And in the last slide, at the last step, we have calculated this delta p minus delta pi, and that's equal to 50.8 atmospheric. So based on this, you can see here that was in gram per centimeter square per second per atm, and multiply by this 50.8 atm. So here what will cancel is atmospheric with atmospheric, because this is on the denominator side and this is on numerator side. So your unit left over are gram per centimeter square per second. So this is flux of water through this membrane. Is it okay? Yes, somehow okay, but in the question he has asked us to calculate this flux in gallon per feet square per day. So let's do that conversion quickly. So this is gram per centimeter per second. So here I have done clearly for you. Again, in the book it is in the confused form, so just follow one by one. This is second, so let's convert it to day because our requirement is day for this unit, time unit. So 3600 second and 1 hour, so you can use this 1 hour against 24 hours per day. So here this second will cancel with the second and hour will cancel with the hour, and your units of time are left over are day. Overall up to here units are gram per centimeter square per day. Now next unit which need to be calculated or converted is centimeter, and 30 point something is, it is usually 30 point something, so I've used here 30 centimeter equal to 1 feet and it's square, so on both sides you will take square, so this will get converted. Multiply by, now last part, that's like gram, and you have to calculate or convert it to gallon, and this is water. You know, this is unit of mass, and you have to convert this to the gallon, that's the unit of volume. So what you have to do to convert all this equation to the unit of volume, you have to divide this by the density, and you can just use this 1000 gram per liter. So by the way, here I have used journal value of 1000 gram per liter, but if you want to go more accurate, you can look at the like density of water at the given temperature 25 degrees C. I think it will be like close to 1000, again exactly not even exactly, it will be close, but that can be used. So here gram will cancel with the gram, and now your units are in the liter, but liter can be easily converted to the gallon because 1 liter is equal to 0.265 gallon. So with this, overall liter is also cancelled, and now your units of centimeter square were already cancelled. Overall units left over are like gallon per day per feet square, and that's 11.5 gallon per day per feet square. This is the flux of water. Up to here hopefully you are clear. This is straightforward, just involve a lot of calculation of this unit conversion. So next is actually salt flux. So salt flux can be calculated by using this formula. Just look at this formula. Overall, if as again I'm repeating same, this is permeance. So permeance value of salt NaCl was given, so here Ni, it indicates NaCl. So this permeance is given, and their concentration on the both sides, feed side and permeate side. Do we have these concentration? Yes, in the form of molarity you have already calculated, and here for this your value is given of permeance in centimeter per second, but this concentration which we have already calculated, and that was in the units of mole per liter. So let's use those and make its difference. So this was in gram mole per liter, feed side and permeate side. For NaCl change in this concentration, I am calculating this CIF minus CIP. This is calculated here, CIF minus CIP. This is 0.313 and 0.0086, which we calculated on last slide, so it will be 0.3044 gram mole per liter, but we have to convert it to the cubic centimeter because you know that the units of permeance of NaCl were given in centimeter per second. So due to this reason I have just made one conversion from liter to cubic centimeter, and this is actually 1 liter against 1000 cubic centimeter. So when you have to cancel this unit, it will be like 1 liter on numerator side divided by 1000 cubic centimeter, and due to this reason you will get this answer further reduced. It is 0.003044 gram mole per cubic centimeter. Now just use this to calculate flux of salt by using this equation. This is value of concentration which you have just converted in the last step, multiply by its permeance, that is 16 into 10 minus 6 centimeter per second. So overall if you cancel the unit here, centimeter will cancel with this, and what you will left over, that's gram mole per centimeter square per second, and this is 4.86 into 10 to the minus 9 gram mole per centimeter square per second. If you remember, he asked us to calculate this in gram per feet square per second. So again we will make here unit conversion. So just start with the first easiest one. Again, this second is converted into day by using these two time conversion. Then there is from centimeter square to feet square. This is similar which we have done initially for flux of water. The only last which we have to make conversion, that is here you have answer in gram mole and you have to report in gram. So this gram mole can be converted. This gram mole means this is unit of mole, and if we just multiply it with the molecular weight, but you will get the unit of mass, because this n multiplied by molecular weight give you the unit of mass of something, of any component. So that we can calculate here. Due to this I have just multiplied it with the molecular weight of NaCl, because I am calculating flux of NaCl. So that's 58.5 gram per gram mole. So this will be cancelled and your unit are finally gram per feet square per day, and that's 22.1 gram only per day through this membrane. So you can see here that that's very small amount as compared to the flow rate of water. That's like 11.5 gallon per day, and that you have seen that it's very small amount, 0.05% in the water. So up to here we have calculated both in NaCl and as well as water flux. So next, the last part of question was about concentration polarization. And if you look at this formula of concentration polarization, as I told you earlier, that this part of the formula is more easier to use, because now you have flux of water, you have value of Ks, only SR you have to calculate, and this will be done. So let's look at this. For this SR, you can use this formula of SP, and for that SP you will need concentration which are already available. But before making this calculation, let's we just this is actually unitless parameter. So for that the units of flux of water should cancel with the units of Ks, and this SR will be definitely unitless, because this SP is the ratio of concentration, so no units. So it's mean we have to just make the units of flux of water consistent with this Ks, and for Ks unit were given, that was centimeter per second, and up to here you have flux of water in various units. So we can just convert. Initially there was one answer of water flux that was given in gram per centimeter square per second, and if I just divide that flux by density of the water, I can just get converted it to centimeter per second. So there is nothing, we just divided that flux of water by the density of the water and we get converted into centimeter per second. So what we have done here, because unit was in gram per centimeter square per second, so we use this density value of density 1 gram per cubic centimeter, and here this gram cancels and centimeter square is cancelled here, and you are left over with only centimeter per second. There will be no difference on the answer because this denominator is only 1. So sometime if you have other units, so definitely it will make any difference, or even temperature change. So if density varies around 1, so it will change, otherwise here it will stay same. Overall its mean value didn't change, only unit have changed. Up to here now only left is SR. For SR let's calculate SP. So SP is the ratio of the concentration of the salt on permeate side over concentration of salt on feed side. So this already you have for any unit you can pick, because unit will cancel, and finally its value is 0.027 here, and with this you can calculate SR, and that's value is 0.973. It's mean 97.3% salt is rejected, only 2.7% salt has passed through this membrane. When you have all these parameter, now Ks was given in the question, flux of water is converted to the same unit, and salt rejection is calculated, so concentration polarization is easily calculated, and that's unitless parameter, and its value is 0.108 for your case, for your question. So that's the value. If you remember, for concentration polarization he said that if value is greater than 0.2 then there is a problem, then you have to change the membrane or the system, or may change the concentration of salt somehow. So but in this case this membrane is suitable and can be used for this separation. That's it. That's the end of RO unit. So RO was discussed in the 2 lecture here, as I introduced briefly in the start of this lecture, that initially from last lecture we know the introduction, working, how RO works, and where RO is applied. Then we started with the, in this lecture, important parameter, that was flux of solvent through the membrane, salt passage, salt rejection, concentration, polarization, and pressure drop. So out of all these parameter, pressure drop is not calculated, that's measured with the experiments, but all other can be calculated, and then we have solved a problem in which we have discussed or utilized all the formulas which are used for calculating those parameters. And I will advise you to just go through all these lectures and then try to solve the problem which are related to RO system, reverse osmosis system, and they involve these similar calculation of like salt flux, there is solvent flux as well, this concentration, polarization, or salt rejection and passage calculation. Okay, thank you.